All right, line A4, we're taking a look at learning task number 5, where we're going to start looking at parallel RL circuits. You should be aware of the fact that almost all the circuits that we go and create in the field are going to be parallel circuits. And there's a number of reasons that we create parallel circuits. The biggest one is that it's not dependent. I don't know if any of you remember having those old school Christmas lights where if you had a single bulb that would fail, you'd have to go through the whole string, replacing one bulb at a time until you found the correct one. It was a total pain. Nobody wanted to go and do that. And it just, kind of took all the fun out of putting up Christmas lights when you knew that you were going to have to go and spend a long time doing that. I don't know, maybe you guys don't remember that. Maybe you guys are all LED Christmas tree generation. But that's the way things used to be done, and it sucked because a single failure point would take out your entire system. In a parallel system, if we have a failure off of a single component, it will take that component out, but it's not necessarily going to take out the rest. Everything else is able to go and operate. And this is really what we want to go and have inside of most applications. Because we are going with a parallel connection, we're also going to go and have a different thing that we're going to go and utilize as being our standardization inside of these circuits. And the different thing that we're going to use will be our value of voltage, because we know that ultimately whatever we have for a source voltage gets dropped across this load, gets dropped across this load, gets dropped across this load. We no longer sum up all of our voltages. Instead, we've got all of our voltages that are going to be seen across each individual component, each individual branch of these ones. As a result, we are going to go and use now voltage as our reference vector. When we were dealing with vectors inside of a series circuit, we used current because we knew that inside of that series circuit we had our inductors, we had our caps, and we had our resistors. We knew that we had that current that was going to be the same through every component. Well, it doesn't actually go through the cap, it goes to and from the plates, but you get what was going on. It was the same value of current that was utilized by each one of these in their calculations. Now what we're looking at is a same value of voltage across each one, which means that the way that we draw everything inside of here is also going to go and change inside of here. Let's just take a look at our sayings that we are utilizing, right? We have got Eli, the Iceman. And Eli the Iceman, if we are going to use voltage as our reference, a reference is simply going to be the place in the circuit that we are going to go and stand on. So let's go and stand on the E inside of each one of these. If I am standing on the E and looking at the I, if my circuit is inductive, I would say that that inductive current that's happening later inside of there, so my inductive current would be lagging in reference to my voltage. Or if I were standing on the E and it was a capacitive circuit, I would say that my inductive current would be happening ahead of it. So it would be leading inside of that circuit. So when we get into doing all of the diagram later on, we're going to start by placing our value of V, voltage, over here. It's an open arrowhead. And then we are going to go and draw anything that is going to be inductive. IL is going to go down there, right? Because our voltage leads, it happens before the current. Our voltage leads, here's that reference at 0, it happens before that current. Same as later on when we get into our capacitance, we are going to go and have our current, IC, that is going to go and lead our value of voltage for these ones. We're not dealing with the current section yet, so we can ignore this for now, but that's why we're changing around where our inductive triangles are. Remember that when we were doing a series circuit, we kept our inductive triangles in the top. Now that we are doing a parallel circuit, we're going to have our inductive triangles that are going to be placed here in the bottom for this. Okay, let's talk about resistances in parallel. Anytime that we go and take resistances and we add them in parallel, we know that we are going to go and have a summing of our resistance that's going to be an inverse, right? Where we're going to go and have less overall resistance because there's more paths for my current to go through. We also know that we're going to be working with KCL at this point. And KCL is Kirchhoff's current law, which states that the sum of all currents that enters a node is any junction, has to be the same as the currents that are going to be leaving that node. So if I take a look, I say I got the total amount of current that enters into this node over here. And then that coming out of that, I've got I1, and then coming out over here is going to be my I2 plus I3. That is going to be going through that line. That's going to enter this node. I2 goes down over there. Oops, I see, that's I3. And then I3 goes down over here, right? We split that I2 and 3 over here. Here we would go and recombine 2 and 3 coming out of there. And then here we would take that combined 2 and 3, combine it with my I1, and we go back up to our IT value. Ultimately, we need to get the same values all the way through. Now, if these were all resistances, the way that they're drawn inside of here, we know that for any type of a voltage that is applied over top of a resistance, we are always, always, always going to go and have our current that is going to go and happen in phase with that. It's going to peak at the same time. It's going to cross down to 0. It's going to peak at the same time like that. We would have in phase for resistive current when we have got any type of a circuit, which means that if I'm drawing out my voltage vector, I'm going to go and have my current vectors that are going to go and be in the same direction. They show that, instead of me drawing, why don't I just go over to what theirs is, they show that on this one over here, where they then go and say, look, we can have the line voltage, and we can go and show that our currents, we'll just place them kind of below instead of superimposing, but we'll place them like that so we see that our line current is in phase with our line voltage. That all makes sense when we're dealing with a with a parallel resistive type of circuit. As soon as we add in the inductance, things are going to get a little bit different. Once again, we have to go and define what is the same for both of these. Well, we see that whatever we've got for a value of voltage is going to go and the same for this voltage is going to be the same for this voltage. Voltage is going to become my reference for that circuit. We are then going to go and have two separate currents. What do you know about this current over here? Well, you should be able to tell me that a resistive current is going to be in phase. In other words, resistive current happens at an angle of 0 degrees. What do you know about inductive current? Well, you should know that anytime I have got an inductive current, EI, my current is going to lag the voltage. So in this case, it is going to be at negative 90 degrees over here, right? Because it's going to be lagging behind that voltage. Here's going to be my I inductive. Here's going to go and be my I resistive. And what we can do is we can vectorially add these two currents. These two currents are going to enter this node. One of them is going to be in phase. The other one's going to be 90 degrees out of phase. Together, they're going to sum up to become a vector sum, where they're going through the main part of the circuit. Then they're going to split into their individual components, 0 degree and negative 90, and then they're going to go and recombine over here to go back to our source as that vector sum that we will have. When it comes to sourcing out our values of currents, we're just going to have to take a look at what our impedances are going to go and be. Our impedances for this one is just going to be the resistance. Our impedance for this one is going to go and be my reactance. And from my impedances, I can create triangles as well. Now, we're going to be very careful with that. We've got a couple of triangles that we can go and create for a parallel circuit. For a parallel circuit, we can create a current triangle. Okay, so I'll just draw triangles up here. A current triangle is perfectly fine for a parallel circuit. A power triangle is going to be perfectly fine for a parallel circuit. A voltage triangle wouldn't exist because all my voltages are the same, right? It's the source voltage over here. We cannot go and create a voltage triangle out of this thing. I can get a inverted impedance triangle out of it, though. And this is going to be a weird triangle over here where we are going to go and see inversions off of it. So we're going to be very careful about using that impedance triangle off of here. If I go take a look, by the way, let me just sketch this right now. This is for parallel circuits that we're going to be taking a look at here. We did go through the series circuits already, and when we went through the series circuits, you should have noticed that we could get a voltage triangle, that we could go and get a power triangle, and that we could go and get a impedance triangle. And there's places where we have to use each one of those. However, when I take a look at what's available inside of my series, and inside of my parallel calculations, you should note that there's only one triangle that's the same that can be used in both, and that's going to be that power triangle. This one here is entirely different. Impedance inside of a parallel circuit is entirely different to impedance inside of a series circuit because it's an inside-out triangle, or what we would refer to as a fractional type of triangle. Let's go and take a look at one of these current triangles here. current triangle is just going to be now my resistive current at 0 degrees, my inductive current at -90, and my vector sum, like that, pointing down now. And then going over to our impedance triangles over here, the same deal. Now, I do want to go and put some values to this because it's a really abstract concept here, an impedance triangle that's going to be inside out. Let's go with a very, very common type of triangle that we would go and have. The 3, 4, 5 triangle. Okay, we'll just put in some values over here. We'll make this side the 4. We'll make this side the 3. And we will make this side over here the 5. If we were to place them in like this, 1 over 5 is going to be 0.2. 1 over 4 is going to be 0.25, right? That's a quarter. And 1 over 3 is going to be 0.33 that we would have for each one of these. That doesn't really make sense, the way that, those values would be placed inside of there for us to go and have a 3, 4, 5 triangle. That is, until we take a look at what this circuit actually is. The circuit is a parallel circuit, meaning that I'm going to have this branch and I'm going to go and have this branch over here. And we know that the total resistance, the total opposition to current flow inside of a parallel circuit is always less than the smallest of these other two sides that we would have, right? A 3, 4, 5 triangle does make sense. If I were to take a look at this, I could see that if I've got, a quarter of an ohm of resistance and a third of an ohm of reactance, that altogether I'm going to have a 0.2 of an ohm of total impedance, right? That makes sense, that we've got less opposition as soon as we place these two in parallel, because there's just more paths. Some of my current goes there, some of my current goes there, like that. However, it gets really tricky if you're trying to do a lot of calculations with it, and you can definitely run yourself into some issues. So I'm going to just suggest right now off the bat, if you're fine with working with one of these, if you understand it mathematically, the relationship, the way that always our impedance is going to be getting smaller by adding in parallel branches, by all means, go ahead, work with these triangles over here. But for the bulk of you that feel like you're taking a drink out of a fire hose as you're going through all of this stuff, second year, all the theory, etc. If you feel like, you're already feeling overwhelmed, leave this one alone. Unless absolutely necessary, do not touch it. I promise you, I will not design an exam question that relies on you having to go and use an impedance triangle in a parallel circuit, okay? Straight up, I promise you that right now, there will always be an alternative way that does not require the impedance triangle. You could use it properly, but it's never going to be required. Okay, let's talk about power. Power triangles are going to be a real thing that we are going to have. Now, our power triangles, you'll note that they don't draw any power triangles inside of this section over here. And if you go through into the next one, learning task number 6, they once again do not go and draw any power triangles into here. And that's because the power triangles, we're going to find out later on, are going to go and break the rules as far as the displacement, how we're going to go and draw those things facing up versus facing down. So they just have not gone and drawn them in. We will deal with those ones later on. When we do deal with our power triangles, just so you're aware of it and it doesn't surprise you later on, VARs L are going to be drawn on the top side again. Watts are still going to stay down here. VARs C are going to be drawn on the bottom side over here. We'll see that later on. Yes, it does not line up with any of this that we're looking at over here, where we've got, anything inductive in a parallel is supposed to be going down to the bottom, but it's just convention that they're drawn like that, and so we're just going to get used to that convention. Power is still going to be able to be calculated the exact same way as what we normally would, which means that really what we'll do for any type of a circuit, just change that so I got a pen here instead, is if I take my value of voltage over top of here, you should remember that we've got this formula, E squared over R. E squared over R gives me a power output, so I can go and get watts by taking my source voltage squared over top of my resistance. I can get my VARs by taking my source voltage, E squared, over top of XL, like that. By taking that over top of there, I can go and get my VARs that I would have for that circuit as well. And really, once I get my watts and my VARs, I can add those two together to get my total VA of the circuit. We can work our way back out from that. We're going to rely heavily on our calculators to go and put these together accurately for us. It's a tool, we might as well use it. And we're going to rely upon power, if and when possible, inside of here. The last section of this talks about the fact that sometimes we have got a practical inductor placed into our calculations. Theoretical inductors exist only on paper. Practical inductors are made out of copper, therefore they have got resistance inside of them. Most cases we see them drawn with a set of dotted lines circling around them like that, which indicates that they're part of the same component. We can't actually physically measure the resistance separate from the XL, the reactance that we would have inside of there. In a lot of cases, we can ignore it, but in a lot of our calculations, we're going to go and have other components that are going to go and act like this. Particularly, what we're going to go and see happening this year is we're going to start seeing motors. Motors that have got resistance and are going to go and have inductance inside of them and are going to act like they were a practical inductor. What we're going to get out of this is we are going to go and get a Z out of this. So what we could get is we could get a Z out of this because it's going to have its own small little mini triangle. If I take a look at the relationship these two have, these two are considered to be in series with each other. Which means I could get an R and an XL, and I could go and have a upwards Z like that. But then I would have to somehow place that Z in parallel with this R over here. That does get difficult to go and do accurately. It's not that's hard to do, it's just hard to keep track of it and make sure you got everything going in the right direction. You could add this thing at the proper angle and this thing at the proper angle of 0 as well, right? Because it's resistive. But why bother with that if that's going to go and cause us issues? Our better way of dealing with these when we get to them is that we are going to, as quickly and as cleanly as possible inside of here, what we should do is convert this to watts. Convert this to VARs. Convert this, E squared over R, into watts as well. And then all that we need to do is we need to go and take our watts of our inductor, watts of our resistor, and we just add those together. WL, WR, and then we're going to go and add in our VARs out. Draw it upside over here. VARs out like that. All together at that point, you would be able to go and develop your VA. And once we have our VA, it's just a matter of using Ohm's law. R is equal to E, E over I, etc. We can go and divide out from our VA. We can use our source voltage, divide out, find our amps. Once we have got our amps and our volts separated, we can then go and use those to go and develop our impedances from them as well. We will do all of these as we get through. Right now, we're just laying out what we're going to do. Once we've established how these operate inside of parallel and established how the capacitance operates in parallel, we'll get around to going through another one of those really beefy types of learning tasks where we've got lots of calculations, just kind of like that learning task 4. We're going to have another one of those that's going to be all for parallel circuits. But that's it for now for our parallel RL circuits. The next thing for us to take a look at is going to be our parallel RC circuit.